So you may remember studying compound interest back in stage 5. So you might remember the formula A equals P 1 plus R to the power of n. We're really going to be looking at here where that comes from. So compound interest is an example of a recurrence relation. Now we're going to see a lot of recurrence relations in the next few exercises. We're just raising the term here really. So $5,000 is invested at 8% per annum, compounding annually. Find a formula for the future value after n years. So we start with $5,000. Our rate of interest is 8% per annum, and we always write that as a decimal, 0.08. Now our n, we don't know. We're finding a formula for n. So after 1 year, we call it A1, the amount after 1 year, and that notation is something you need to use a lot and get used to. So A1 means after 1 year. So after 1 year, we've got the $5,000 that we started with, plus we've got some interest on that. So 0.08 times the 5,000 is the interest. If you factorize out the 5,000, we've got 5,000, one lot of 5,000 plus 0.08 lots of 5,000. Okay, and if I just simplify those brackets, that's 5,000, 1.08. Okay, now that already is starting to look a bit like this formula that we had up here. So for n equals 1. Okay, and that formula is the same thing. Okay, let's look at what happens after 2 years. So after 2 years, we've got the amount that we had after the first year, plus we've got the interest on that amount. Now that there gives our recurrence relationship, and it's really important to write that line in the coming chapters. So I'm really starting it now, that is very important. Okay, so this was our A1. So I'm just going to factorize it first before I put any values in. So we've got our A1, one lot of A1 plus 0.08 lots of A1, sorry. I already wrote the A1, I don't need it again. So equals A1 times 1.08. Now A1 is this value here. So instead of A1, I've got 5,000 times 1.08. That's my A1 times by this. Okay, so we can see there that that's our 5,000 times 1.08 squared. Again, we can see how that relates to this formula that we know from stage 5. Let's do the same thing for after 3 years. It's exactly the same. So after 3 years, we had the amount at the end of 2 years, plus we had some interest on that amount. Okay, let's factorize it. So A2 at the front, 1 plus 0.08. Simplify the brackets. So 1.08. And then let's replace this A2. There is a really good reason I'm following this particular process, because when we get to harder problems later on, we need to know this process very, very well. So instead of A2, I need all of that. So A2 is this. That's our A2 times by 1.08. And if I use my index laws there, that's my 5,000, 1.08 to the power of 3. 2 there, 1 there, make 3 altogether. So I can now say, what's that after n years? I can follow my pattern. So when it was A3, that power was a 3. So this pattern is very obvious. When it was 2 years, the power was 2. 3 years, the power was 3. So when it's n years, I'm going to get 5,000, 1.08 to the power of n. Now, just to look at our recurrence relationship, we can write this in terms of an or an an plus 1. There's a couple of different ways to write it. This an is how we normally do it, but I'm going to look at both. So an, we're really just writing this line here. So it's it's a with n minus 1. Okay, that was 3, that was 2, that's 1 less, so n minus 1, plus 0.08 times our a n minus 1. That could also be written where we just add 1 to each of these. So it could be that the next one is the last one plus 0.08 times the last one. It can also be factorized, so 1.08. But this is the one we're generally going to use because we're generally going to be asked for a formula for AN. So our formula, as I said above, now we can do it with these letters. So the amount at the end we call the future value, the principal is the present value, the R is the rate per period, and the N is the number of periods. Straight from here, that the future value, okay, AN, is equal to whatever we had at the start, the present value. This is 1 plus the rate of interest to the power of the number of time periods.